we construct a hash using iterative method, wherein we are splitting the entire message into blocks of 512 bits. Now over here we can see if there is a shortcome in the number of bits, if it is not a multiple of 512, in that case we append the message. So the message is appended with a padding, and then this padding is in terms of 150. Okay, so actual message, along with that we have a padding. The padding starts with 1 followed by any number of zeros required to complete the constraint of a multiple of 512. And along with that we use 64 bits to represent the length of the message, length of the actual message. So that, moving further, over here we can see the construction, the entire hash. So we have the actual input that is given to the hash, that is the message that is given to the hash, along with the initialization vector. So now we can see that over here we have said that SHA has 80 rounds. In order to convert a given input to an output, it uses 80 rounds. Now each of this round is grouped into 20 steps, or 20 rounds are grouped together to call a step. Now 80 rounds are divided into 4 steps or 4 stages. So this is the first 20 rounds, this is the second 20 rounds, this is the third 20 round, and the fourth 20 round. Now the given input is divided into 5 blocks. Now 512 when divided into 5 blocks gives us 64 bits. So each will take 64 bits. Now over here, even in the other end, we have the initialization vector, and we divide this initialization vector into words, and each round of SHA will take one word, that is 32 bits. So this A is 32 bits, B is 32 bits, C is 32 bits, D is 32 bits, and E is 32 bits. Over here we are taking a input of 160 bits. So now, moving further, we have seen that the output of the first 20 rounds is given as input to the next 20 rounds. This process works iteratively. Finally, when we get the output which is stored in all the registers, we perform a integer addition and then addition modulo of integers, and we get the hash value. So we'll just see this diagram in detail now. Now initially what we need to do is we need to have one word for every round, and in order to have one word for every round, we divide the 512 blocks of 512 bit initialization vector into 16 words, and each word is 32 bits wide. Now these 16 words populate the first 60 positions. Now how do we look at this? Over here in this diagram, see that there are 80 words required for 80 rounds of SHA1. Now word 1, word 2 up to word 16 is obtained directly from the initialization vector, and each word is of 32 bits. Now there are 80 rounds, hence 80 words are required. So now how do we get, as told earlier, W1 to W16, that is first 16 words are directly obtained from the initialization vector. So now the question is, how do we obtain the words from W17 up to W18? So for that we use this or the equation. So for any given round, if you want to calculate a word, let's say it is round T. So WT for the word for this particular round is equal to WT minus 16, WT minus 14, and then WT minus 8 and WT minus 3. So for let's calculate, let's see this example. In order to calculate the word 16, we are using WF0. So W16 minus 16 will give us WF0. So this value is already known to us because we are directly taking it. Okay, over here we can see that the first 16 words are directly obtained from the initialization vector. So W0 or W1 over here. Okay, W0 is already known to us because first 16 words are known to us. The next is W2. How did we obtain this W2? Now W16 minus 14 will give us W2. Now W0 is XORed with that of W2. Now next word is W16 minus 8 that needs to be XORed with this. So W16 minus 8 will give us W8 and then WT minus 13. So W16 minus 3 is W13. So when we XOR all these 4 words, we get the 16th word. Okay, for our reference, we have considered that it is from W0 to W15. So we have calculated for W16. So similarly, we can calculate for the last word also. So any word after W0 to W15 can be calculated using this particular equation. I hope this is clear. Now this we call as array initialization of words. So this is a set of words that are required to be supplied to each round of SHA. So there are 80 rounds in SHA, hence we need 80 words. Now once we are done with the calculation of the words which are required for SHA, let's see what happens in the actual algorithm. So we will see this literature later. So let's look at this diagram. Now the input of ours, which is 160, and it is divided into 32 bits and 5 blocks of 32 bits. So we get A, B, C, D and E. All these are registers where we are storing the bits. Now the first now over here we can see we are let us try to relate this particular round to Fistel cipher. Okay, what do we do in this Fistel cipher? The entire block of input is divided into half and then we work on each halves separately. In the first one we work on the right half and keep the left half as it is, then swap it and then perform the operation. Same way we have performed over here, but it is sort of unbalanced Fistel cipher. Over here for all these blocks, so this main input is divided into 5 blocks. Now over here we are applying B, C and D to the function f. Now the output of this function f is then we perform addition modulo with that of the value in E. Okay, now we get an output for this particular operation f. Addition modulo is performed over E. So what do we mean by addition modulo? In case of addition modulo, we supply an input of 32 bits and another input of 32 bits. But here, this is 32 bits. E is giving us 32 bits and the output of F is again 32 bits. When we add these two values, we may get a carry. If we get a carry, we simply drop it down. So, and just retain the rest of the bits. Such an addition we call as addition modulo 2 raised to 32. Now this addition is done. This is not XORing. Now over here, once we get this, so we can observe here the bits in A register is shifted, and it is shifted by how many bits? It is shifted by 5 bits. We perform a left circular shift of 5 bits. So what happens to the 5 bits that are shifted to the left? They are added back to the front. So still we get a 32-bit value, and this 32-bit content of the A register, which is shifted by 5 bits, is then added to the output which we just obtained. Now the output of this addition is again added to what? We are adding it to the word that we have calculated just previously, and then depending on the round which we are working on, we add that particular word. Once the word is added, then we apply a constant. We add a constant to this and then Okay, this is the entire process of dealing with the input and getting the output. Now we have got an output after this in this red operation. We got an output of 32 bits, and this 32 bits are placed in the register A. Now the question is, what do we place in the other registers, and why not this particular input goes directly to E? It is because next time also again only on the contents of E and BCD function will be working, and the hash calls for a property of uniformity. The output should be obtained equally from all the input bits, and that is why we are performing this particular swapping of the bits. So over here the output that is obtained is placed in A, and then the content of A is placed in B, and then the content of B is shifted by 30 bits, left circular shift by 30 bits, or you can say 2 bits right shift, and it is placed in C, and the content of C is directly placed in D, and then the content of D is placed in E. This is the swapping that happens. Now continuing the next steps or the next round, this will form the input of it, and same thing can be repeated. This is what happens in each round of SHA. Once this is done for 80 times, we get the hash value. The same thing, it is written in terms of code. You can see that initialize 5 registers S1 to S5, wherein we are storing the input. Once the input is stored, what do we do? Now we need this input. What is this input? It has a message along with the pad and the field length. We have already discussed as to why we need padding and why the input has to be in multiples of 5 and 2 blocks. Now, create an 80-word array. Now we have seen how to create that 80-word array using the equation WP. I think let's just get back to this. We have to create this entire array using this particular method of array initialization. So first 16 words we directly get from the initialization vector. Subsequent words we need to calculate. Once done, what do we do? For all the rounds, we perform this operation. So first what do we do? We have, as explained, F5, I'm applying the function F over S2, S3 and S4. That is contents of S2, S3 and S4. And then what am I doing? To this, I am adding the contents of S1 register, which is shifted by 5 bits, and then I am adding also the contents of S5, and then these are all, we have represented it as A, B, C, D, E, rather than representing it as A, B, C, D, E. Over here it is represented in terms of register S1, S2, S3, S4 and S5. S1 represents A, S2 represents B, S3 represents C, S4 represents D and S5 represents E. So over here, this I'm adding, this is a constant which I'm adding it to the output of output over here, and also I'm adding a word. We can refer to this diagram for clarity. And then where am I? This is the positions where I will store the output. So S4 will be stored in S5. What does that mean? D is stored in E. And S3 is stored in S4, and so on, as we have discussed. I think this is evident from this particular diagram. Moving further, now just to ponder over the literature of the SHA algorithm, we have discussed that SHA1 has 80 rounds, and SHA1 has 4 stages: stage 1, stage 2, stage 3 and stage 4, and each stage has 20 rounds. The first stage has rounds 0 to 19, second stage has from 20 to 39, third one has from 40 to 59, fourth stage has from 60 to 70. Now the question arises, why are we staging these particular rounds? Why not continue as a single one? because the function that is applied for the first 20 rounds is different as compared to the function that I apply to the subsequent 20 rounds. And the third stage, fourth stage, all the functions in these 4 stages operate differently. Now let us look at the difference. Now the function f(x,y,z), where do we apply this function? Let's see this diagram. Over here, this function is applied on the contents of 2, 3 and 4 registers. So over here we can see that what is that we are using. Let's say this represents 2, 3 and 4 registers. Depending on the step we are working on is defined as follows. So for the rounds 0 to 19, this is the operation that is followed. The contents of register S2 is ANDed with contents of register S3, and then over here negation of contents of register S2 is ANDed with the contents of register S4, that represents S4. Now the output of both of them is again XOR. Similarly, the contents of S2 is XOR with the contents of S3 is then it is XOR with the contents of S4. That is, the 3 registers whose input is passed to the F function is XORed for next 20 rounds, that is round 20 up to round 39. Then similarly we perform this operation for round 40 to 59, and then the XORing operation of all the 3 registers for round 60 to 70. I hope this is clear. This gives a reasoning as to why we need to divide the entire 80 rounds into 4 stages. Okay, now looking back at the diagram, now this diagram will make a lot of sense. Now when you look back at this diagram, you see that each of the stages that is represented as that represents 20 steps will take the function f1, that is the function that is defined just now, f1. Along with that we have a constant k which is same for first 20 rounds, and then we have a word w. We apply word w 0 to 19 for the first 20 rounds. Then moving further we apply the function f2, a new constant k2 for the next 20 steps, and the word from 20 to 39 from the from the array. And then we have the third stage wherein it involves again 20 rounds with the function that is applied over here for the registers B, C and D, or S2, S3 and S4 is F3. Along with that we have a new constant K3 which is applicable to the third stage 20 steps, and then we have word 40 to 50 words that from the array 40 to 59 are used for this particular. And similarly for these, the output of all of these registers is again we perform addition modulo to the given input, and in order to get the actual hash of 160 bits. Okay, we were working over here. Now all the four stages will take these functions and operate according to these particular functions. Now moving further, after having understood SHA1, we will try to see where exactly SHA1 is applicable. So there are 2 applications for SHA1 or SHA algorithm. One is hash-based MAC and the other one is digital signature. Let's see the working and the difference between both the hash-based MAC and the digital signature. So in case of hash-based MAC, we come across a question as to how can a cryptographic hash be used to provide features like message authentication and message integrity. Now what is message authentication? Message authentication is a property wherein I am able to say that a message has come from a particular source. And message integrity is a feature wherein a receiver is able to say that the message is not altered during transit or transmission. So for that we use hash-based MAC. In order to achieve these two features or properties, we used hash-based MAC. So I think you people have studied MAC in the previous sessions. MAC stands for Message Authentication Code. And over this Message Authentication Code, we will calculate this using hashing. Now there are two ways in which I can calculate or compute this hash. One is keyed hash MAC and the other one is HMAC. Now let's take a scenario wherein we have a sender and a receiver. The sender needs to generate a MAC and send it to the receiver, and the receiver, upon receiving the message and the MAC, should be able to verify these two properties of message authentication and integrity. Let's see this scenario. Suppose a sender and a receiver share a secret key. Now the key is shared between both sender and the receiver. At the sender side, let's see what happens. Now we generate a string by concatenating K and the message. That is, a key and the message are concatenated in order to generate a string. Now over here we have represented M as the message and key as K, which both of which are concatenated. Now the second step is find the MAC by calculating hash over this particular string. Now this first step gives us message concatenated with the key, and over this particular string that we have obtained after concatenation, we need to perform a hash. So over here we will use the SHA1 algorithm. Once we calculate the hash over the message, over the string concatenated through message and the key, we get the MAC. We append the MAC to the actual message and transmit it to the receiver. We just don't send the MAC. We append it with the message and send it to the receiver. Upon receiving, the receiver should be able to verify what? He has to be able to verify authentication. Along with authentication, he has to be able to check whether the message is integral. So these two features, we'll see how he verifies. Let's look at this diagram. The message, we are performing hash. Hash is also called as compression function, to which, first we are, okay, let's avoid this diagram. Okay, at the receiver side, what is happening? On the receipt of the appended message with the MAC, what do we do? Can we reverse the hash? No, it is having a one-way property, because we are not able to get back the original message. So we need to calculate MAC at the receiver. So find the MAC using the same procedure that was used by the sender. What is that? Generate a string by concatenating the key which is available at the receiver. We have assumed that receiver and the sender both are aware of the secret. Now generate the string by concatenating the key and the message, and then over this perform the hashing. Once we perform the hashing, we get the MAC. This MAC is calculated at the receiver end. Now compare the MAC generated at the receiver with the MAC received from the sender. Okay, we compare the sender's MAC and the receiver side MAC. Now this entire process is done at the receiving end. Once this is done, we need to check whether there is a match between the MACs which from the sender and the receiver, or there is an unmatch. If there is a match, it means that the message is obtained from the source in a proper manner, or we are able to achieve message integrity. If it is an unmatch, that means there is some sort of tampering that has happened to the message. Now the question still continues over here. What does the match or unmatch of MACs mean? Match means we are able to achieve source authentication. How we are able to achieve the source authentication? Because the secret key between the sender and the receiver is known only to sender and the receiver. Only to them the key is aware. Now what is message integrity? Message integrity is message should not be changed during transmission from the source to the sender. Now are we able to achieve it? Yes, if both of them, if both sender MAC and the receiver MAC matches. If we have seen the property of avalanche effect, right? If one bit of input is changed, the ripple effect or the avalanche effect on the output is enormous. Half the bits of the output change, get inverted. So, yeah, if there is a match, it means the message is authenticated. Along with that, it is integral. If there is an unmatch, we do not accept it. We say that the message is tamped. So, moving further. Next question is, in what way are the properties of cryptographic hash relevant to the security provided by the MAC? Yes, they are relevant because we are able to achieve both the one-way hash property over the MAC. We are not able to reverse the MAC because we have used hashing. Another one is collision resistant. Both the properties we are able to achieve even with the help of MAC. Now, why a MAC is based on a hash function? So why can't we have seen, right, we have used that chaining method of generating hash, wherein we use the DES algorithm and then generate the output and pass it as input to the next step. So in this method we generate the MAC value. But over here, the question is as to why we need to use a hash rather than using the conventional method. Because hash operations are faster as compared to that of the encryption and decryption operations. And then the hash function, the crypto hash function code is easily available to us. Now moving on to, this was the first method wherein sender and the receiver were sharing a key and then performing the computation of MAC and verifying whether the authentication and integrity is achieved. The next is HMAC, hash MAC. Now this is another method of computing MAC value which is based on hash. Over here, let's see the drawbacks of the previous method and then see why this method was actually proposed. So MAC, which is calculated using keyed hash, had a message concatenated with the key in order to obtain the hash. There was a weakness that was found with this. And what was the weakness? We had to share a key prior to the communication. So always in symmetric key cryptography, we have observed that sharing of key is a big issue. So we had to move on with the another method called as HMAC. And this HMAC was developed by Bellare Canetti Hugo in 1996. And it uses cryptographic hash function with the combination of secret. Let's see how this is done. Let's see this diagram. I have taken a snapshot of this from your textbook. Over here, we have the initialization vector or the key itself acting as a initialization vector. Now, instead of concatenating this key with the message, what is done over here is we pass this key or the initialization, which acts as an initialization vector to subsequent operations. We'll see this operation by checking on equations. So first what we have done over here, the key is XORed with iPad. Over here we are using two pads or two types of padding. One we call as iPad and the other one we call as OPAD. Now over here M stands for message. Let's try to understand the notations used here. K stands for the initialization vector or the key, and then iPad stands for iPadding, OPAD stands for OPADing, and then M stands for the message. iPad is nothing but a hex value, which is hex 36 value, which is repeated 64 times, and OPAD is hex value, which is repeated again 64 times. Both are different values, hex values, which are repeated multiple times. It is 64 times they are repeated. Now over here M stands for the message, H stands for the hash. And over here we can see the H is again a hash, and we have, after entire operation is performed, we get the H mark. So let's try to understand this diagram. We have the key which acts as an initialization vector, and we subject it to XORing with the iPad value. Okay. and then once this is XORed with the iPad value, we get a output which is again concatenated with the actual message, and then we perform hashing over this particular concatenated message. Now after this we need to wait for the other end to work. So same key is passed as input, which is XORed with the contents of OPAD, or which is padded with the key, and the output that is obtained is again concatenated with the output of the previous step. We perform second hashing in order to get the H mark. Let's try to understand this in terms of equations. Now the key is padded with zeros to form a 64 byte string denoted as K dash. Since key K is padded with zeros, we denote it as key dash or K dash, which is XORed with the constant denoted by iPad. So over here we have key which is having padded with zeros in order to get K dash or K1. Now this K1 is then XORed with the constant value of iPad. So iPad is XORed with that of K1, and we get what? Result 1. So in this diagram we are obtaining result 1 here. Now further, it is then concatenated with the message and a hash is performed on the result. So message along with the result that we have obtained previously, both are concatenated. Message and the result obtained previously are concatenated to get the result 2. Now where is this result 2 in the diagram? Over here. Now after obtaining result 2, what is performed? Hash is performed over the result 2 in order to get result 3. Now let's see where this result 3 is. Now over the result 2, a hash is performed in order to get result 3. So result 3 is here. So we need to work on the other end now. Now K dash is XORed with another constant after which it is prepended to the output. So first what are we doing? K dash or K1 is XORed with the constant value of iPad on the other end, and we obtain the result 4. Over here, K dash is XORed with the content of OPAD in order to get result 4. Now what do we do with the result 3 and the result 4? We need to concatenate it. So the result 3 and the result 4 are concatenated in order to get result 5. Now remember, result 4 is prepended. So it is prepended with that of the result 3. It is attached in the front to that of the result 3 in order to get result 5. So once again, hash is computed in order to yield us with HMAC. So over result 5, we are performing a hash in order to get HMAC. So moving further, so this is about 2 ways of generating HMAC. One is with the use of a secret key at both the sender and the receiver, but sharing of the key was found to be an issue. And in the second case, we are using 2 times hashing in order to make it more stronger. This is a stronger HMAC as compared to the previous one. Now moving further to the applications of hash, we have digital signatures. Now the question arises, what is the difference between HMAC and the digital signature? Once we discuss the digital signature, we'll see the difference between both in terms of the services and the properties provided. Okay. Digital signature uses a secret key known only to the sender, that is the sender's private key. Over here, if we use a RSA digital signature, and let's say A is Alice on the message M. So over the message M, I'm applying an encryption key. Now digital signatures are able to provide us with 3 properties. One is sender authentication can be achieved, message integrity can be achieved, and non-repudiation. Now we are aware of what is authentication and integrity. To brush back as to what is non-repudiation, let's say there is a sender and the receiver. Sender sends a message to the receiver. The receiver upon receiving may deny that he has not received the message, and the sender may also deny that he has not sent the message. So both the denials should not be possible in case of non-repudiation. Non-repudiation has two types. One is denial by the source and denial by the destination. Denial by the sender and denial by the sender is wherein the sender denies that he has sent a message. Denial by the receiver is what? Wherein the receiver denies that he has received the message. So it should not be possible. So these three properties can be achieved with the help of digital signature. So over here on the message, actual message of which is generated by the sender Alice, we are performing a hash. In order to achieve a digital signature, first we perform a hash and then encrypt it. Regular encryption is what? Over the message we perform the encryption using Alice private key. Over here what are we doing? We are first hashing the message and then encrypting it using Alice private. Why are we doing this? Because the size of the message is very huge at times, but when you hash it, you get a fixed size length of the message, or the hash message is always, hash value is always fixed size. So encrypting that is easier than encrypting a large message. So we are performing this operation. Now the question is how to verify this particular signed document. Okay. I perform the reverse process at the receiving end. And how do I perform the reverse process at the receiving end or the receiver side? I just use Alice public key, which is available to people in the network, and decrypt it. Okay, and decrypt it in order to obtain the hash of the message. If there is a match, that means the message is integral. That is, it is not altered during transit. You are also able to see that the messages come from the source Alice. How? Because we are using Alice public key and private key for encryption and decryption. And the third one is what? We are able to say that the message has come from the source itself. Okay. Now let's before moving on to the performance, we will see that the difference between HMAC and the digital signature. In case of HMAC, we are just able to achieve two properties. First property is message authentication. We are able to authenticate that the message has come from a legitimate source, and message integrity. That this feature says us that the message is not altered or tampered during the transit. These two features can be achieved with the help of HMAC. This is one application of hash function. Now another application was what? Digital signature. Digital signature is a better version of application of hash function, wherein we are able to achieve three properties. One is message authentication, and then message integrity, and the third one is non-repudiation. The first one is able to achieve just two properties, and the second one, that is the digital signature, is able to achieve three properties: extra non-repudiation along with authentication and data integrity or message integrity. Moving further, I think we have 3 more minutes time. Moving further, we'll just try to complete this, or at least one more topic. Moving further, with the performance of hash as compared to the previous encryption algorithms that are discussed, let's see their performance. Computation time required for SHA1 algorithm as compared to DES, an encryption algorithm, and then RSA. Okay. In case of SHA1, over here we see that the time taken is somewhere around 1844 seconds. In case of DES, with an input of 128 bits, and RSA with an input of 1024 bits. So DES for encryption. Now SHA for hashing, it is taking 1844 seconds of time, microseconds of time. Encryption for DES taking how much time? 3,900 microseconds. So there is lot of difference between the time taken for SHA to calculate the hash value and the time taken by DES to encrypt the input. Similarly, the time taken for decryption is 4,000 microseconds. And the time taken, the other counterpart is the RSA algorithm, which takes an input of 1024 bits. And over here, the encryption is 5,20,000 microseconds. I think it is like multiples of whatever, lot of time as compared to that of SHA and DES. So after comparing this, we are able to see that SHA is an efficient, gives us more efficiency as compared to that DES, to that of DES. And now, can we take off some questions? How do I? Okay. I think if you have any questions, you can just leave it on my email ID. You can just take down my email ID and leave the questions on my email. Thank you. In the next session, we will be discussing about, we'll continue our discussion on performance. We'll discuss birthday attack and start off with the discrete logarithm introduction and the algorithms involved. Thank you for today.